Hello, Mark Smith here, also known as Smitty Halibut, KR6ZY, although soon to be N6MTS. We'll talk about that in a second. I am here happy to present at the BayCon 2021 event on February 6, 2021. Today I'll be talking about the W6NBC Double Delta Slot HF antenna and how I built and tested one. So who am I? Well, my name is Mark Smith, currently, or aka Smitty or Smitty Halibut. Currently, my call sign is KR6ZY as I record this, but I'm hoping to be N6MTS by the time you see this video. On Twitter and YouTube, I am Smitty Halibut. You can find me there. Twitter's probably the best place to get a hold of me. What are we going to be talking about today? Well, this double delta slot HF antenna. I'm going to give you the background of why I'm giving this presentation today and what goals we're going to try and to meet with this presentation. We're going to talk about how I built the antenna, how I took the measurements, how I analyzed the antenna from those measurements, and what conclusions I've drawn. And then we'll talk about what's next. So first off, background and goals. So what is this antenna? Well, it's an antenna that was designed by a gentleman named John Portune. His call sign is W6NBC. He's written many articles in many different publications, such as QST, CQ, etc., etc. Several years ago, he got an interest in slot antennas. If you remember an article in QST where you could take a satellite TV dish, like one of the Dish TV kind of network, Dish Network kind of TV slot, dish antennas, and then cut a slot in it with a little vampire teeth hanging down on the side and use it as a VHF antenna, like a 2-meter antenna. That was his article. He wrote that article. Last year at the QSO Today Ham Expo in 2020, he presented on an HF slot antenna, and he gave a great presentation. It's one of my favorites. The article for that presentation is at this link here, W6NBC.com. From there, you navigate to articles and look for his article on the double delta slot antenna. I'm going to be talking a little bit about that antenna, but really for all the details, go see his presentation or read his article. So why this antenna? Why do I want this antenna? Why am I interested in it? Well, it's got a lot of really neat features. It's got a small footprint, like a vertical antenna, right? It's built like a vertical antenna. Very small footprint on the ground, very tall, no ground plane, except that it radiates like a horizontal dipole at the elevation of the top of the antenna, which is pretty rad. It's multi-band. Sort of. It's non-resonant, so you use a tuner to make it multi-band, but that's what we're going to be talking about today. But it'll operate on a wide range of bands, and it's electrically steerable, electrically pointable. There's no rotator. There's no physical moving parts other than the relay to be able to change what direction it's radiating in. So it's got a lot of really neat features. Sounds pretty great, huh? Well, let's go take a look at it. What are the goals for this presentation? I blame George because we were talking about this antenna on the Ham Radio Workbench. I think it was on the podcast. And he started asking all kinds of questions for me that I didn't have answers to. Like, one of the questions is, how do you build it? You got two loops. They're physically 90 degrees out of phase from each other. And John doesn't really answer this question of whether you put those loops in parallel or in series. He doesn't even talk about how to analyze it. But what do I mean by parallel and series? Well, parallel and series, right? You got a north-south loop and you've got an east-west loop. One's pointing north-south and the other one is pointing east-west. When I say pointing, I mean broadside, which way they radiate. And they don't actually have to literally be north-south and east-west. They can point it whichever way you want, but I'm going to call them the north-south and the east-west loops. You could literally put them in parallel like this, or you could connect them in series. They'll work the same either way. The impedances will be different, and the job that the antenna tuner has to do is different. But electrically, the radiation pattern of the antenna is the same in either of these cases. The other question is about rotation. 90 degrees isn't very precise. I can either have it point that way or I can have it point that way. And my question was, if I energize only a single loop, not both loops, I can also add the 45s between those 90s as a radiation pattern. So let me tell you what that looks like. When you got two loops, so here's our north-south loop and here's our east-west loop. In the sides of the loop that are in phase, both of the same phase, that's where the radiation is going to go out, right? So that plus and that plus, they're going to constructively interfere with each other going that way. Same with the minus and minus. They're going to constructively interfere this way. But the plus and the minus on this side are going to destructively interfere going out that direction. So this is the null. These are your radiation patterns. If you electrically reverse one of them, just swap the leads, that's the minus and that's the plus. Now the plus and plus are down here. This is your in phase, and that's where it's going to radiate. And your in phase is out here, and then this is where your nulls are going to be. So just by reversing the polarity of one of the two loops, you have rotated your antenna by 90 degrees. That's pretty slick. But would it be helpful to also have the 45s? If I only energize one of those two loops, right, then it just radiates like a normal loop, and it goes broadside of the loop that's energized. So the east-west is turned off here, but the north-south is energized, and so it radiates on the broadside. If you do the same thing with the east-west, it radiates the other way. And so in these 4 different configurations, you could have all 45-degree radiation pattern options. So George was asking me a bunch of questions. Is one of these options, either parallel or series, better than the other? If not, can we build the antenna so that it can use all available of these options? And then, is it worth the added complexity to do that? And that's what I'm going to be trying. Those are the questions I'm going to try and answer today. So that's the background and the goals. Let's go build the antenna. One of the cool things about this antenna is that the dimensions are not critical because it is non-resonant. The tuner will match it to whatever the antenna is within limits to what the radio wants to see, to the 50 ohms the radio wants to see. It doesn't matter whether it's exact dimensions. We're not resonating the antenna. So you can build it in just about any way you want. Hand wavy. In my particular case, I had a 24-foot section of 2x4. It's actually a 20-foot section with a 5-foot section kind of overlapped by about a foot screwed on top of it. So from ground to the tip, it's about 24 feet. I'm using lumber because that's what I had. If you have a metal mast, that works just fine as well. It does not need to be non-metallic for the mast. My base, my balun, is about 2 feet off the ground because it makes it easier to work on. So the total height of the antenna is about 22 feet. The spreaders at the top of the mast are 4-foot sections of fiberglass tubes sticking out, like half-inch fiberglass pipes, and that I run the wires through. And since they stick out from the mast by about 4 feet on either side, the total spread at the top is about 8 feet. The balun down at the bottom is a 1-to-1 balun. It's just 11 turns of speaker wire on an FT140 43 toroid. The tuner is an LDG RT600 remote tuner. Again, all of the details of building this are available in John's article. I'm just kind of hand-waving and describing how I built this antenna. The feed line, because of where it is in the yard and where the shack is and how the cable runs, it ends up being about 200 feet. I had RG213 around. There's a big story about how good that cable is or whether it's good or not. I ended up buying some DX Engineering 400 Max to replace it with. I have not replaced it yet, but the spool of cable is in my garage. I will be replacing it before too long. So that's what I built. Here are some pictures of it. So this is a picture down at the bottom facing upwards, so you can see the 2x4 mast. It's bolted to the corner of my fence. There's a steel fence post right behind it that's about 2 feet into the ground with concrete. So that's how the mast is anchored. Here's the matching box. You can see the wires going up, the spreader up at the top there. This is what it looks like when you're looking at it from the yard. So it's at the corner of the fence. This is the balun box. It's just SO238 coming in here, turns on a FT140 43, and then goes up to the stainless steel screw terminals for the wires coming down to up to the antenna. About a 3-foot section of coax over to the RT600 tuner, and then what's not shown here is the feed line going into the tuner over to the shack. All right, so pretty simple build. The spreader bracket at the top is something that I had to design custom. This is a OpenSCAD parametric model. I 3D printed this bracket. It fits right on top of a 2x4 with some screw holes that you can screw into the 2x4 to keep it in place. Then it's got these 4 brackets here for the fiberglass masts coming into them, or spreaders. And then the wire goes in through the hole there, and then out through the top, up and over into the next one, over to that spreader there, right? So the wires kind of cross over each other on the top of the model. I could have made the spreaders go straight through all the way across and then just made them one on top of the other so they're not coplanar with everything else. I opted for this. I'm not entirely sure why. It's somewhat arbitrary. But this model, both the OpenSCAD source code and the STL are available on that GitHub. So all of these files, all this data that I'm showing you are on GitHub. Okay, so, oops. I built my antenna a little bit differently than the way John describes it. So W6NBC's design is radio to feed line, to balun, to the tuner, to the antenna. All right. I built mine radio feed line, tuner, then balun, then antenna. So you'll notice that I swapped the order of the balun and the tuner. What's the implication of this? Well, in John's design, the tuner is on the balanced side of the balun, even though it is an unbalanced tuner. Okay, that's not ideal. It works, but it's not great. I, on the other hand, have the tuner on the unbalanced side of the balun, but now my balun, which is designed for 50 ohms, is now being used in a circuit with wildly varying impedances and very complex impedances, right? I have not done the analysis to figure out how well my balun's going to work in all of those situations. Probably not as great as I would like it to. Both of these are compromises. Neither one of these is a great design. I am going to go ahead and proceed with my design because, to be frank, I didn't find out that I screwed this up until very late in this process. I had already collected all the data and done all of the analysis. I'm going to proceed with what I've built because it works. It's got its issues, but it works. All right, so that's my oops. That's the antenna build. Let's look at the measurements. How am I measuring it? Well, I'm going to use everybody's favorite new tool, is the Nano VNA. I have a Nano VNA F, the larger one with the 4-inch screen. I recommend the 4-inch screen for us guys whose eyes are getting older. Anyway, hopefully you saw Alan's presentation earlier today. Even though I'm recording this several weeks before the event, I'm sure it was awesome. Actually, all of Alan's stuff is awesome. If you haven't seen him on YouTube, go check him out. Hopefully you saw his presentation earlier today on the Nano VNA. Because of that, I am not going to go into details. I will mention that I had some fun adventures in Nano VNA calibration. There was a lot of a learning curve on how to calibrate over the right frequency range and all kinds of fun things like that. So took me a while to figure that out. I took a lot of bad data, removed it from GitHub. It's all in the Git history if you want to go take a look at it, but it's all junk anyway. So the stuff that's still in GitHub right now, currently in GitHub, is all good, taken after properly calibrating the Nano VNA. In addition to the Nano VNA, I also used a software package called Nano VNA Saver. It's a software package. It runs on Windows, Mac, Linux, and it adds a lot of functionality to the Nano VNA. It just uses the Nano VNA for the hardware. It uses it as a sensor, and then it talks to it over a USB cable, controls the Nano VNA, gets the raw data from the Nano VNA, and does its own analysis internally. One of the big advantages to Nano VNA Saver is that you can configure it to do multiple segments. A Nano VNA will only measure 101 data points from the start to the end frequency. If you tell it to measure between 3 and 30 megahertz, it's still only going to measure 101 data points from 3 to 30 megahertz, and that's not great precision. I wanted to measure from 3 to 30 megahertz in about 10 kilohertz steps. So I configured it to measure from 3 to 30.27 in 27 segments of 101 steps each. Hand wave. You got to jump through some hoops, but 2,727 steps of 10 kilohertz each will measure between 3 megahertz and 30.27 megahertz. I got that whole thing in 10 kilohertz steps. What is it measuring? It's measuring the S11 parameters, not the S21. That's different. The S11 parameters. What is an S11 parameter? Hopefully Alan explained this better than I will, but put a signal out this port 1, hence the first one, actually the second one. The output is 1 on port 1, and then we're measuring what's coming back in from port 1. So input on port 1, output on port 1. That's why it's S11, the 1-1. We're outputting a signal, then we're measuring the amplitude of whatever signal comes back, and we're measuring the phase, the relative phase of whatever signal comes back. The fact that we're measuring the phase is what makes this a vector network analyzer instead of a scalar network analyzer. If all we were measuring was the amplitude, that would be a scalar network analyzer. All right, and then NanoVNA Saver saves all of this data in a standard file format called Touchstone. The file extension is .s1p. If you're measuring S21 parameters, where it's out on one port and in on a different port, that would be an S2p file. We're only using S1ps, or the S11 parameters. NanoVNA does a lot of visualizations. It is a very useful tool in and of itself. It's neat to visualize that data. We're not going to be doing that very much for this data. I'm primarily interested in those Touchstone files. But this is what NanoVNA looks like, right? So it's super useful. Up here is where you set that sweep. I was talking about the 27 segments of 101 steps each. This is where you configure that. You can set up a bunch of markers, what frequencies. I've got them in the centers of each of the bands. Here's what's showing the data at those markers. You can tell it what data you want it to display for each of those markers. I've got a bunch of graphs on here, the Smith chart of what the antenna looks like, the complex impedances, yada, yada, yada. A lot of really cool stuff that you can do with NanoVNA Saver. This is not a presentation on Saver. So I use the NanoVNA and Saver just to take the measurements and save it to a Touchstone file. Next thing we need to do is we need to analyze that data. And that's where a lot of my fun stuff comes in. So what are we analyzing? Well, what does the antenna look like natively? That's what the Touchstone file has, right? The complex impedance of the antenna at a given frequency. And it's got a whole lot of those frequencies. It measured it every 10 kilohertz, between 3 and 30 megahertz, right? So let's calculate what the theoretical perfect matching network would be at that frequency to match that impedance to a 50 ohm resistive load, which is what the radio is expecting to see. What is that theoretical perfect matching network? All right. My RT600 is not a perfect tuner. It is not infinite. It does not have an infinite range of capacitance and inductance values, and it does not have an infinitely small precision, right? It can count from 0 to 127 in 10 picofarad steps. So from 0 to 1,270 picofarads. Or it can count from 0 to 127 in 100 nanohenry steps. So from 0 to 12,700 nanohenries, right? So it's a 7-bit switching network of 10 picofarads or 100 nanohenries. And that's what it can do. And then the inductor is in series, and then the capacitor is either in parallel with the source or with the load. It can move the capacitor to either side of the inductor. So it's an L network. It's a low-pass L network with a capacitor on either side of the inductor. That's what the RT600 can make. So now that we've limited the theoretical perfect matching network to what the RT600 can actually produce, what is the impedance presented to the radio based on this real matching network and the actual impedance of the antenna, right? It's not going to be 50 ohms because we've got some limitations on the tuner. So let's go figure out what that impedance is when it's presented to the radio. That number is ultimately what we're going to be looking at the rest of this trip. So I wrote a Python script to figure all of this out. There's a lot of calculations. We got a lot of data points. I started out like copying and pasting values into an online calculator, and I very quickly realized, no. I just wrote a Python script that does this for me. So the Python script takes in an S1P file and outputs all of this. You'll note that the first column here are the measurements. This is what's in the touchstone file. So we got the frequency that we're calculating at. What are the complex impedances at that frequency? Then we calculate the amplitude of the impedance and the SWR. Then we calculate what the ideal matching network is. If the capacitor is in parallel with the source, then it'll show up in this column. If it's in parallel with the load, it'll show up in this column. And then the inductor is just always in series, so it's always there. Then we apply the limitations of the RT600 to that matching network. We limit it at 12,700 nanohenries and at 1,270 picofarads, and then also to 100 nanohenry steps or 10 picofarad steps, right? So this is the matching network that the RT600 can make to get as close to this ideal as possible. This here is an alarm that says we're out of range. We need way more inductance than what we can provide. So this says we are out of range on the inductance. In the other data, some of the data below that's not on the screen here, we are out of range on capacitance as well. Then, given this actual tuning network applied to this complex impedance on the antenna, what does the radio see? Right? That's what we're showing on this last column, and that's what we are interested in for analyzing this antenna. Given this network and this complex impedance, this is what the radio is actually going to see. Okay? That's what we're doing. I'm not going to show you all the raw data here. That screen was just to demonstrate what my Python script had done. If you want to see the actual data, go to my GitHub. It's all there. What I am going to present here are the conclusions. So I've taken a look at all of this data and I've looked through it and tried to figure out tried to answer George's questions based on that data. But first, a disclaimer. All of this is based on my particular build of this antenna, right? One of the big features of this antenna is that it is very flexible in its construction. The dimensions are not critical. The antenna tuner will match whatever you build to your radio, mostly hand wave, right? If you build your antenna with different dimensions than what I built, your numbers will be different. I'm not saying that you have to build your antenna exactly like I built mine so that these numbers match yours. What I'm saying is build the antenna that you want to build for whatever your constraints are or your capabilities are, but use my tools that I have published and made them freely available on GitHub so that you can measure your actual antenna and analyze your actual antenna and perform this same analysis for your use cases. Okay, so what are the actual conclusions for my antenna that I built? And here are the different bands, the different qualitative analysis based on the parallel, the series, and the single loop. And then some notes on here. This slide is in the slide deck. You can go read it. I'm not going to go over every single one of these pieces of data, right? What I am going to do is answer this question. What does it all mean? Well, in parallel, with loops in parallel, we get a good or great match pretty much from 60 meters to 10 meters, with the exception of 30 and 20. It's a little reactive on 30 and 20 meters, but the tuner inside your antenna, or the tuner inside your radio, will be able to match the reactiveness of the SWR on 30 and 20 meters. The SWR is still pretty low. It's just mostly reactive instead of resistive. In series, we get a good but not great match on 60 meters and 15 and up. The match is great on 30 meters. And again, it's usable but very reactive on 40, 20, and 17. Right? So you can already see how the series is good on 30 meters, but it's not good on, but 30 meters is not good in parallel, right? So it's good on series, but not on parallel. But if the opposite is true for 40 meters, it's good in parallel, but not in series, right? So now we have a case of two different bands where one is good on one, but not on the other, and then the other one is good on the other, but not the one. So this is why you might want to put the switching in the base of the antenna to select the configuration, parallel or series, based on what bands you're operating on at any given time. And then single loops for the 45s. It's good or great from 60 to 10, except, again, for 30 and 20 meters. In the parallel, you could kind of make it work on 30 and 20. It's within range, but just very reactive. It is an unusably high SWR. It's above 3.0 to 1 or higher on 30 and 20 meters for a single loop. So the single loops are great for everything except 30 and 20 meters. I haven't used the antenna a whole lot because I just got it working a few weeks ago, and I've been super busy with work. But I have done some testing, and what on-air testing I have done matches this data. I'm seeing on bands that it says it should match super clear. The radio is saying, yeah, 1-to-1. On bands that it's saying I should have about a 2-to-1, I'm seeing about a 2-to-1. So it's matching pretty close with this data. That makes me confident that this analysis that we're doing is going to be pretty good. So what is this antenna good at? Well, it has all the benefits that John mentions in his presentation, in his article, right? Small footprint, horizontal radiation polarization out of a vertical antenna, all that fun stuff. In my case, it covers all bands from 60 to 10 meters at varying degrees. It might also work on 6 meters. I don't know. I haven't measured 6 meters, but I can't think of a reason why it wouldn't also work at 6 meters. It's pretty easy to construct. It's inexpensive, except for that tuner. It could be made portable, but more field day portable, not so much soda portable. What's it not good at? Well, again, as built in my yard, 80 meters and below is pretty much a complete loss. The SWRs are high enough that I'm not likely to be using it on 80 meters anytime soon. If you built your loop taller or wider or larger in some way, you could probably fix that. You could probably make it work on 80 meters. I can't think of a reason why you wouldn't be able to. 20 meters, one of my favorite bands, is not great in any of the configurations. It's usable, but it's pretty reactive. Using the tuner in my radio, I can probably compensate for that because I have, but it does mean that I need to use the tuner in the radio, which when you've got a remote tuner, you're kind of not supposed to do. Is it worth the complexity for having parallel and series? If I cared strongly about 30 meters, I could see building a switching network here to change between parallel and series. But for my use case, I don't use 30 meters very often. I'm not a CW guy, and I can do FT8 on 20 and 40 just as easily. So I'm willing to trade 30 meters in exchange for a simpler build. So I'm going to keep mine 2 loops in parallel and just use the parallel configuration. It means 30 meters is not great and 20 meters is not great, but it makes it a much simpler system. Someone with different goals, or if you build your antenna differently and you end up with different numbers, I could very easily see someone justifying this complexity. The complexity isn't great, isn't huge, but for my use case, I don't think I need it. But someone else, I could easily see justifying that. So, is it worth supporting single loops to be able to get those 45s? This one's a little bit harder. Would it help? Would it even help to do that? Well, the modeling that John did shows that the antenna is down about 3 dB, 45 degrees off from center, right? So if that's the radiation direction, 45 degrees off, you're about 3 dB down. So the total beam width is about 90 degrees at a minus 3 dB range. So rotating it by 45 degrees would only get you about 3 dB worth of benefit. 3 dB is not nothing, but it's not huge either. The side nulls are a lot narrower, so it might be worth trying to point your antenna more precisely to be able to null out a noise source or a strong signal or something. So I could see someone trying to get it for that. Can it be done? Well, the single loop is pretty similar to the parallel. It's good from 60 to 10, except for 30 and 20, although it's pretty much unusable on 30 and 20. The SWR is really high. Should it be done? The RT600 is a memory tuner. there's a term for it, that has a memory. So when you transmit on a frequency for the first time, it goes through its full process, 10 or 15 seconds of switching out all of the relays, trying to find the perfect match. And it finds the best match for that given frequency, and it stores it in memory. And then you go off to some other frequency and do something else and have to retune it. And then you come back to that frequency, and it says, aha, I've already tuned on this frequency. I remember what the matching network is. And it goes straight to it, and it says, yep, that's still a nice low match. Perfect, we're good to go. And so it goes straight to that matching network that it remembered from last time. But if you've changed your antenna from parallel or from a dual loop antenna to a single loop antenna, that will inherently change the impedance of the antenna on a given frequency. And now you've lost the benefit of that memory in your tuner. So now your tuner has to go through and perform a full retune every single time. I found the tuner to be more of a pain in the butt than I anticipated, and anything that makes it even less convenient is not a good thing. So for me, for my personal use case, I don't think it's worth bothering with the complexity to add single loops. Even if the complexity weren't all that much, to me it's not worth it. So, summary, for my antenna at my use case, I'm going to keep them dual loops in parallel. I'm going to put a remote switch out there to swap the phase of one of the two loops so that I can rotate it by 90 degrees. I am not going to bother supporting series or single loops for my personal build. Again, as built that way, it will cover 60 meters through 10 meters to varying degrees. 20 and 30 will require a little bit of additional tuning in the shack, but for the most part, it's okay. And I'll probably make a second one of these for use with my club for field day. I think it would work really well as a field day antenna. All right, so those are the conclusions I've drawn. What is next? All right, so let's say you built your antenna differently, or you have different goals, and you do want that complex switching network. What would that look like? Well, I drew that up. Again, this diagram is also in the GitHub, so all of that data is there. With these 4 double pole, double throw switches, we can get full configuration of the antenna. These two switches, switch 1 and switch 2, turn on and off each of the individual loops. By default, they are normally enabled, normally closed, I guess. So the loop is in the circuit. You energize one or the other of these two relays to take that loop out of the circuit. Switch 3 changes the two loops, changes the loops from it being in parallel to in series. And then switch 4 reverses the phase of one of the two loops for that 90-degree rotation. So with these 4 switches, or these 4 relays, you can completely configure your antenna for any of these configurations that we've talked about. Bonus points. If you run the power for switch 1 and switch 2 through a third pole of switch 3, so that when you energize switch 3 to be in parallel, it removes power from switch 1 and 2, you create a safety interlock. So whenever you have these in series, you want to make sure that both the loops are always there in series, because if you make one of the loops go away, then now you've got an open circuit. So you want to make sure that both of your loops are there for in series. And if you run the power for these switches here that take the loops out of the circuit, and turn that power off whenever that relay switch 3 is engaged, you create a safety interlock. I highly recommend you do that if you're going to do that. So make this a 3-pole or a 4-pole relay here to be able to cut off power to these two. So there's the switching network you would build if you wanted to. You can design a board with like an SO239 at the bottom, a little spot for a ballon in there, all of the relays you want, and then terminals for the loops up at the top of that. If you really want to get fancy, you can control it with a microcontroller on the board to control all those relays, and you can make it so that it knows all of the different configurations. You just tell it, I want, on this band, and I want to point in that direction, and it, does all of the relays for you to figure that out. You can even control it using George's fancy serial protocol, his RS-485 over a Cat5 cable, or wirelessly over Zigbee if you have a way to get power out to the thing. In addition to that, John is continuing to work on this antenna design. He's got more coming. He's continuing development. I won't steal his thunder here. I know what he's doing. It's pretty cool. but I'm going to let him talk about it. So I strongly encourage you to go watch his presentation at the QSO Today Ham Expo in March of 2021. He's giving a presentation there. And that's it. I promised there would be notes at the end, a slide with all of the links. Here it is. And I will take time to answer any questions. Again, I'm Smitty Halibut. Find me on Twitter or YouTube, and thank you very much for watching.